Good morning, everybody. In this lecture today, we will cover the topic of radiation physics, the physical stage of radiation action. So this is the first slide. We already described the concept of dose, the most important quantity in radiation biophysics. The dose is defined as the energy per unit of mass, and the unit is the gray. However, there is another concept which is sometimes used, which is slightly different from the dose. While the dose is the energy absorbed in the volume, the kerma is defined as the kinetic energy released in the matter. So it's the sum of the initial kinetic energies of secondary particles in the volume. What is the difference? Of course, the units are the same and they look like very similar quantities. But if you look in the next figure, you see what is the main impact that you have between kerma and dose. If you plot the dose as a function of the depth in the absorber, you have a phenomenon known as build-up. So initially you have a build-up in the dose, and then you have an exponential decrease, which is what you essentially expect based on the absorption of the of radiation. But if you plot the kerma, you don't see the build-up, because of course now the kerma is all the kinetic energy of the secondary electrons. So even if the secondary electrons deposit the dose, the energy, in a deeper layer, and that's why you have the build-up phenomenon, you don't see this build-up in the kerma. So that's when you use the kerma and when you use the dose, you have to be careful, because you see the depth dose distribution will not be the same. So how many ionization we have in our body? How many ionization we produce normally in our body? And let's only focus on the ionizations due to ionizing radiation, of course, not in general. So as we saw in the previous lecture, we have about 3 millisievert, which is, however, about 1.5 milligray because of the high quality factor of the radon gas. And actually 1.5 milligray, if you do simple mathematics, is 1.5 millijoule per kilogram, which means 9.4 per 10 to the 15 electron volt per kilogram. Now, the average energy per ionization is about 34 electron volt. So we're talking about something around 34 electron volt. So this means that we will have something like 2.75 per 10 to the 14 ionizations per kilogram per year. And of course, if you take an average person of 70 kilograms, this means 6 per 10 to the 6 ionizations per second. So you realize that the number of ionizations ongoing in our body only because of the background radiation is extremely high. So ionization is not a rare event. But you can say, okay, but if we think that radiation is dangerous, then why you have so many ionizations and there is no problem? Because the effects of radiation are not due to the individual ionizations and not to the total energy deposited, because this is easy to demonstrate. The lethal dose for a human is about 4 gray. You remember, we saw this last time in the plot. Now, the energy absorbed by an average man is then 4 joule per kilogram times 70 kilogram. This means 280 joule, but that's only 67 calories. 67 calories is like drinking a cup of coffee, you know, because drinking a cup of coffee, you have a delta T of approximately 20-23 degrees. And this means that in 3 ml, you have the same energy of 67 calories that you have with ionizing radiation. So it's not the energy is not a thermal effect, of course, is a much more specific effect due to the quality of the damage induced by ionizing radiation. This we will see, of course, but one of the main problems in this course will be that at the end you have to understand why the radiation is so dangerous, even though if you look at the energy deposited, it is actually very small. Now, this we already saw, the electromagnetic spectrum, of course, and the ionizing radiation is up here for high frequency, for photons. And the first thing we will see today is the generation of X-rays. So how do we generate, how we produce the X-rays? Now, normally the production of X-rays is done in tubes. Essentially, you must have some way to accelerate electrons. These electrons that come from a cathode, in this case, you see this is a cathode, one, the number one, and they hit on the other side, this is the anode, so they hit the anode on the other side, and they are essentially stopped here, they slow down, but then they produce radiation by Bremsstrahlung. This Bremsstrahlung radiation is called, is the X-ray. So the spectrum, the typical X-ray spectrum that comes from a tube has this shape. You see, there is the Bremsstrahlung spectrum that generally is filtered. So this is why there is a threshold. If there is no filter, the Bremsstrahlung spectrum, this is the intensity as a function of the energy, will have this behavior. This is the highest energy of the electron, which means what is the maximum voltage of your tube. In this case, typically is 150 kilovolt. Sometimes it's 250 kilovolt. That's, of course, is the maximum possible energies when essentially the electron stop and release all his initial energy in a Bremsstrahlung photon. But on top of the Bremsstrahlung spectrum, filtered so that you stop the low energy component, you have lines, and these lines are instead characteristic lines due to the atomic structure. So they correspond to specific photons due to the emission in the atomic shells of the target. So Bremsstrahlung, you know what does it mean? Essentially, this is a general phenomenon that applies to every charged particle. When there is an acceleration or deceleration, because that's generally a deceleration, this is associated to emission of photons. It's a consequence of the Maxwell equation. So you know this quite well. That's how it looks like generally. So you have an electron. It's important to point out that for the conservation of the momentum, the emission of the photons must happen in the field of an atom, so that you have this electron now in this field will change its direction, and there is the emission of a photon. Of course, the frequency of the photon comes from the Planck equation, so it's the difference from the initial kinetic energy of the electron and the final one, and the maximum possible energy of the photon will be EU, where U is the tube voltage. This is called the impact parameter. Now, the energy loss by Bremsstrahlung is very well characterized by this equation. It's kind of apparently complicated equation, but in reality it can be simplified very much because it's simply the energy loss minus VE divided by rho x. So this is an energy loss per unit mass thickness. So rho x is in grams per square centimeter, is the mass thickness. We will use, very often we will use mass thickness instead of mass, and can be easily described as E divided by x0, where x0 is the so-called radiation length. Now, the energy loss goes with declines with the square of the mass. And in fact, this means that essentially it is only significant for electrons. So when you go to hadrons, there is Bremsstrahlung, of course, but we will never consider Bremsstrahlung as a significant source of energy loss. It will be all by electromagnetic interaction. So for low energy electrons, you can simplify the formula. You have that d on the x for Bremsstrahlung divided by the total d on the x is approximately given by the energy in MeV times the atomic number of the target divided by 1000. So this is a simple formula, but useful because you see, for example, if you have 100 kilovolt electrons on a tungsten, a typical target, so the atomic number is 74, about 0.74% of the energy lost is converted into X-rays. So this is relatively low even for electrons. You can imagine that it's totally negligible for hadrons. The angular distribution, you see, is given by this formula, is the square of the sinus of the angle. So it is kind of directional. Is not really random. The emission, you see, it goes more into the forward direction and is as much in the forward direction as we increase the energy. Instead, of course, the non-continuous spectrum, the lines in the X-ray spectrum, come from the structure, from the atomic structures, and you know this very well from quantum mechanics. This is given by the transitions that are regulated by the Rydberg law, and you have the Lyman series, the Bellman series, and so on, depending on where is the transition, between which lines is the transition occurring. So this is giving lines, and of course, because it depends on the levels, you will have different lines if you change the target. This really depends very much on which target you use. Another important effect for radiation biology is the so-called Auger effect. So you see, what can happen is that when you have a transition from one shell, for example, from the L shell to the K shell, this is the nucleus of the atom, you have the emission of a photon, which is actually an X-ray. Okay, but in some cases, to the decay from the L shell to the K shell is not associated the emission of a photon, but the emission of an electron. Of course, a low energy electron, because that's only the energy that correspond to the difference between the L shell and K shell. But this low energy electron, because they are low energy, we will see, can be biologically very effective. So it is important to know what is the ratio, the so-called fluorescence yield divided by Auger yield. So how many Auger electrons you have as compared to the photons that you can produce. And you see that for light targets, like in tissue, you have a lot of Auger effects. So you can produce a lot of Auger when you have a light target. This means that when you have electrons in the tissue, you have to consider the production of secondary electron as Auger as an important source for the biological damage. However, for the production of X-rays, you go to high Z, material like lead, wolframium, tungsten, and so on and so forth. And in this case, you see eta is almost 1, so you have mostly production of X-rays. Now, the interaction of photons with matter, of course, in this course, the issue is not so much the production, which is really for nuclear physics, but the interaction that you have of this radiation with matter. The mechanisms of energy transfer are essentially related to the inelastic scattering, because of course the elastic scattering, when you have no energy transfer, we will see it's very important, for example, in radiotherapy, because in radiotherapy you want to focus your radiation on the tumor, so the elastic scattering is having an impact on the focusing of the beam on the target. But from the damage point of view, the only thing that really matters is the inelastic scattering, because with the inelastic scattering means there is an energy release and there is ionization. So for photons, these are the processes that can happen. Coherent scattering, as I say, is this kind of phenomenon. The photon comes and has scattering, but no energy loss. The Compton effect, instead, you know, is an inelastic scattering, where you have ionization of an electron. In the photoelectric effect, you have the absorption of the photon and emission of the electron. In the pair production, you have a high energy photon that essentially in the field of the nucleus disappears and generates a pair. And finally, in photodisintegration, you can have a photon that interacts with the nucleus and can eject neutrons or protons from the nucleus by interaction. Now is a Compton effect, but not with the electron, with the hadrons in the nucleus. So essentially, you have these. We will see that Compton is the most important, but we will briefly see all of them now. Generally speaking, how is described the absorption of X-rays in matter? As every time you have an electromagnetic radiation, you have impact of n0 photons through the X. You write the usual equation, the n as minus me and x, so that the decrease is proportional to the number of photons, and this is a classical differential equation whose solution, as you know, is an exponential. So the number of photons is always given by n0 e to minus me x, where me is the absorption coefficient. To be precise, you see, you can define it in many different ways. For example, the cross section for the interaction, you can write it as me divided by this quantity rho Na by A, which is the number of atoms per cubic centimeter. If you think of rho is the density, Na is the Avogadro number, and A is the mass number. So this quantity sigma is called cross-section, and this is very important. I mean, we will talk about cross-section all the time in this course. The meaning of the dimension of the cross-section is square centimeter. Or barn. We will see when we talk about neutrons. In nuclear physics, we use another quantity which is 10 to minus 24 square centimeter is the barn, and is essentially the product of the area of the sensitive target times the probability that one particle through the sensitive target induces the effect. In this case, for example, we are talking about photons. Interaction of photons with electrons in an atom. So the cross section, the area here is essentially the surface of the atom, if you want. And then the cross section gives you the probability that one photon going through an atom can induce ionization, for example. So we will see the cross section, and you see, of course, cross sections and absorption coefficient are strictly related. They are essentially the same quantity. I mean, you only have to normalize the absorption coefficients to the number of atoms per unit volume to have the final cross section. So it is also possible, you see, to write is more common in a way to write this formula in this way, where you essentially define the mass absorption coefficient in square centimeter per gram, and you multiply it by x rho, which is the areal density of the target. This is normal in our field because, of course, if you change the density of the target, of course, you will increase the interactions because you have more atoms per unit volume. So the photoelectric effect is, I'm sure, very well known to all of you. It consists essentially in the absorption of a photon. So a photon is completely absorbed, and the energy of the photon is spent in ionizing the atom. So the energy of the electron is essentially the energy of the photon minus the binding energy, because of course you have to overcome the binding energy. If the energy of the photon is exactly the same of the binding energy, you will produce an electron with zero kinetic energy. The spectrum, you see, this is the cross section for photoelectric effect as a function of the energy of the photon. And you see that you have very characteristic lines. These lines correspond, of course, to the quantum structure of the energy levels of the target. So they are unavoidable. You will always have lines here. But the general trend, apart from the lines, is like E2 minus 3. So you have the absorption coefficient decrease very strongly with the energy. You can imagine that. I mean, if you increase the energy, the probability of absorption of the photon immediately decrease. It's much more likely that the photon will scatter on the electron, going into a Compton effect, for example, rather than being absorbed, considering that the energy levels in the atom are relatively slow. So the photoelectric effect decrease quickly with the energy, like approximately like the energy to the third power. This is an example, you see, of the angular distribution that you have for the photoelectric effect. Again, when you go to high energy, you tend to have a forward peak. But the important thing also to consider is that apart from the energy of the photon, it depends strongly on the material target, and of course becomes much more likely if you have materials with the high atomic number, because then you have many electrons, and then you increase the probability of having absorption in the atom. And in fact, you see the dependence on the Z that goes like the atomic number to the fourth or fifth power. So for light elements, like in biological tissues, the cross section goes down. But it's important when you have heavy targets. The Compton, I already told you many times, so I'm not going back to it. Is of course is an inelastic scattering of the photon generally on external shell electrons, to the point that generally the binding energy, which should be considered in principle, is even neglected, because generally the binding energy of the external electron is so small and the energy of the photon is so high that you can essentially neglect the binding energy and say that the initial energy of the photon is the sum of the kinetic energy of the electron and the energy of the scattered photon. Now, how to derive the Compton effect, I will not do it, because really, I'm sure you have done it in many basic courses. It's a classical example, you know, of it's generally the first lecture on quantum mechanics, shows how the photon can actually interact with an electron like a billiard. So you know very well, I mean, the classical derivation that comes essentially from the Planck equation and the energy conservation and momentum conservation, both in X and Y axis. And you certainly remember that the minimum energy transfer when you have the energy of the electron, the kinetic energy of the electron is zero. In this case, no change in the energy of the photon, and this corresponds to an angle, scattering angle of zero, while the backscattering, which is 180 degrees, so when the photon is completely backscattered, in this case you have the maximum energy transfer, and the energy of the electron is given by this formula, where epsilon is the ratio of the photon energy and of the electron mass energy. The cross sections for the Compton effect are not very easy to calculate. I mean, it's very easy to calculate, you know, the angular dependence of the Compton effect. But if you want the cross section as a function of the angle, that's much more complicated. So I'm not going into detail. I only want to show you that this can be done. It's called the Klein-Sheena energy transfer cross section. And let's say it can be simplified in this way that gives the fraction of energy transferred to the electron. So we know the cross sections, how to calculate the cross sections. Now, this is the fraction of the incident energy retained by the photon as a function of the energy of the photon. Now, this is interesting because you see that the range of energy here goes from, in this plot, goes from 0.01 MeV, which means 10 kilo electron volt. This is 100 kilo electron volt, 1 MeV, 10 MeV, 100 MeV, 1 GeV. Now, generally, X-rays, as we have seen in the production of X-rays, you use acceleration of the electron in a range between 100 and 300 keV. So you are approximately here. Gamma rays are generally between 1 and 2 MeV, so they are around here because they come from the nuclear shells. You can actually have photons at much higher energy if you accelerate the electrons much more. There are, for radiotherapy, sometimes people use 25 MeV electrons, so it's a very high energy electrons. So you go even in this region, and then you see normally, let's say in this region of X-rays, gamma rays, if you see, this is the fraction of incident energy absorbed by electron. You see, normally for X-rays and gamma rays, we are talking about some 50%. If you take very energetic X-rays like those produced in Linux for radiotherapy, then you can have a much higher energy. I mean, the electrons take up much more energy. This is a consequence of the Klein-Shina formula. And of course, you have an angular distribution also here, which again is not random at all. This is the angular distribution of the photons, and this is the angular distribution of the electrons that you see depending on the energy. This is epsilon, so it's the ratio of the energy of the photon and the mass energy of the electron is kind of in the forward direction. Then we have the pair production. The pair production is another typical typical quantum effect. It can happen when you have only when you have photons with energies higher than 1 MeV, because it must be higher than the sum of the mass energy of the electron, which is 511 kilo electron volt. So let's say mass times c square for an electron is 500 kilo electron volt. So if you want a photon to disappear into 2 electrons, actually, of course, because the photon has 0 charge, it cannot disappear in 2 electrons. It has to disappear in a positron and an electron so that the charge is still 0. The energy of the photon must be higher than 2 times MeC squared, which means more than 1.02 MeV. And as usual, if you want to conserve the momentum too, this can only happen in the presence of the nucleus. So this only happens into a nuclear field. The photon disappears, and you have a positron and an electron. The positron, of course, will annihilate with an electron, depending on the energy, in a very short, depending on energy and material in a very short range. So we'll annihilate with an electron and create another pair of photons at 511 and 11 keV. The cross section for pair production is proportional to the square of the atomic number of the target. And finally, we saw in the movie this photonuclear interaction. That's a bit strange, if you want. I mean, it's something that is not always studied. It's essentially is a high energy photon that now is having a Compton effect, if you want, not with an electron, but with a hadron in the nucleus. Generally, what is particularly interesting for us is the gamma N reaction. So when you have a photon that produces a neutron, This is, you see here, I mean, is not very, you see, this is the cross section as a function of the photon energy, and this is another one for different material. This is in copper and this is in lead. But you see that essentially there is a threshold depending on the target. You see the threshold is different for the target, but there is a threshold that high energy, so around 6 MeV. Below this energy, it's impossible. It can happen. Of course, the photon must be really energetic. So here we are only talking about very high energy photons. I mean, not gamma rays coming from nuclear, from natural radioactivity, because the energy is always lower than 6 MeV. But if you produce X-rays and very high energy for radiotherapy, what can happen is that you interact with the material in the head of the beam delivery, in the so-called nozzle, where photons are directed into the patient. They interact with the walls of the nozzle. They produce neutrons. These are typical spectrum of the neutrons. You see, depending on the energy, this is 31 MeV, 15 MeV, and 13 MeV photons, and you see the spectra of the neutrons. That's the neutron energy, and that's the frequency, the neutrons per MeV. You can produce neutrons, and so you think you irradiate your patient with gamma, but you are in reality you are also producing neutrons that can go everywhere in the patient. So this photonuclear interaction is a problem for radiotherapy. And you see only for radiotherapy, because it only occurs when you have very high energy photons interacting with the heavy materials. So this is, you see, an example of the depth dose profile for different energies. And you see that this is the depth, this is the dose. If you move from low energy, this is cobalt 60, for example. Cobalt 60 is 1 MeV photons naturally emitted by cobalt. If you increase the energy of the photons, the slope becomes less sharp, is more shallow. And this is good. If you remember, I have to irradiate from different angles because the normal tissue is here and the tumor is here. If the that dose distribution is more shallow, my dose distribution will be better. But you see, after 6 MeV, you gain, but you also produce photoneutrons. That's something you have to remember. So we saw all these effects. Let's put now together, and let's look at the cross-section. The absorption coefficient here is the same as the cross-section, and let's compare it. So this is now the absorption, the absorption coefficient per unit divided by the density, so it's in square centimeter per gram, the mass absorption coefficient, as a function of the photon energy for the different effect. You see, photoelectric in green, Compton in blue, Paarbildung, this is pair production in black, and the total absorption coefficient is in red. So you see, when you go to low energy, you see in this region here, below 100 kilovolt, so when you are in the low energy, the absorption coefficient for this is in water, so that's in the material that we are interested in. The photoelectric effect is actually dominant. So if you have low energy X-rays, photoelectric effect is important. When you have very high energy photons, you see this is in the order, this is 1 MeV, this is 10 MeV. When you are in the order of 100 MeV or 70 MeV, very, very, very high energy photons, then pair production becomes important, because the most important process. But this is very seldom, because, you know, the gamma rays are here in the order of 1 MeV, and the X-rays are here in the order of somewhere in between 200 and 500. If you want to go to radiotherapy, then the energy goes a little bit up, let's say here, but even here, you see, even in this region, let's say between 6 and 10 MeV, the Compton effect is the most important. So that's what I was telling you also last time, that the Compton effect is the most relevant process in radiation biology. So that's the consequence for radiobiology. The consequence for radiation effects is essentially that you have, for the ionization of the molecules, X-rays. We're all talking about X-rays as yet. Using either photoelectric, Compton, Auger effect, or even eventually pair production will release binding electron. You have the production of high energy electrons, and these high energy electrons can undergo further interactions. This goes, let's say, in the how the charge, but now this is not anymore a photon. So the photon by definition has no charge. The electrons have a charge. So now we enter in the world of the charge-charge interaction, so in the world of the Coulomb interaction, while so far, you see, for photons, of course, the interaction is not Coulomb interaction. And in fact, I mean, what we can see now is how the electrons interact with the matter. We do this before the charged particles in general, the ions, because I want to make sure, because actually you will see that also charged particles eventually produce electrons. So it's important to see first the electron interactions in matter. As usual, as for everything, you can have elastic scattering, but this is important for therapy, for example, because you lose the electrons, but not so much for radioprotection, for example, where you are interested, of course, in the inelastic scattering. Inelastic scattering can be excitation, of course, and ionizations. Very often excitations and ionizations are counted together because the consequence of the excitation can be the emission of an Auger electron, as we have seen before. Elastic scattering, and this is the excitation that we have seen, of course, also for photons, but this can also happen with an electron. And finally, ionization, where essentially you have the emission of a new electron that was in a shell is now a free electron. Now, how is the cross sections of interactions in tissues? You see, this is now the cross section as a function of the energy of the electron in kilo-electron volt. And it's divided. You see, this is the elastic. In blue is the elastic. In green is the excitation that has some fine structure here at low energy. And ionization is in red. So the first general rule you see in the blue line, you get the general, this is a log-log scale, right? So it's not a linear scale. Now, always remember the cross-section has a tendency to decrease with the energy. This is normal, you know, because the cross-section means the probability of interaction. So if I run very fast in a party, if I go very, very, very fast, I will have little opportunity for shaking hands, for interaction. Let's say in these times of lockdown, one could say, if you see a crowd, and of course you have to keep social distance, well, you better run, because then your interaction, your cross sections will decrease, because you go to high energy and you will have no interaction and you will get no disease. However, you see there are exceptions. For excitations, you can have specific fine structure due to the atomic structures. And of course, for ionization, you have a threshold, because you must have energy enough to release the energy. So you have a threshold, then you have a raise phase, and then you go into the normal region of decrease. So these are experimental data. It's not easy to measure the cross-section of electrons in water, but this has been done. And you see, the important thing that you can get from this model is that when you have electrons around 100 electron volt, this is the maximum of the cross-section. Because at lower energy in water, I'm always talking in water, that is the target more important for us from the radiation biophysics point, the radiation biology point of view. Below this energy is actually too low, so you will not have a strong effect. At higher energy, you start to decrease the cross-section because, of course, you enter in a region where the interaction is less likely. Now, this is described by the famous Rudd equations that are also quite complicated. As you see, this gives you the electron ionization cross-sections. I don't, as for the Klein machine, I don't want to go in detail. I only want to show you that you can actually calculate the cross-section of the electrons for as a function of the energy of different materials and so on and so forth. And that's again a comparison of different models with some experimental data. You see the Rudd models is this one, and then there are other models you see that are no, I'm sorry, this is the Busis model. This is the Rudd models with the relativistic data. This is interesting. You see the cross-section as a function of the electron energy here in this comparison of different models. All models, you see, agree that around 100 electron volt you have a decrease. You have a maximum of the cross-section. Then you have a decrease. Then at this energy, you enter the relativistic region, and then you have a raise in the cross-section again, and that's because of the time dilatation. When you go into the relativistic region, I told you that when you run fast, the time of interaction with the people around you is decreasing, so you will not get the coronavirus. But if you run so fast that you enter in the relativistic region, the time is changing, is dilated. I mean, you have the expansion of the time in the relativistic region, and then this is not decreasing anymore, and you have a sort of flattening here. All theoretical, though there are no experimental points here. Please note this. The electrons also have a lot of elastic scattering, and then as a consequence, you see that this is actually an experimental image of the electron path in a cloud chamber, and that's how it looks like. You see, you can have a lot of events. You can have Bremsstrahlung, and you can have ionization with emission of other electrons. These secondary electrons, if they have enough energy to produce further ionization themselves, are called delta rays. So we have alpha rays, alpha particles, beta rays that are electrons from the nucleus, gamma rays that are photons from the nucleus, and now we also learn a new word, delta ray. Delta ray is again electrons, but they are not electrons from the nucleus like beta rays, are electrons from the atom, and they come from secondary ionization, and they can induce ionization themselves. So at the end, we can calculate another thing, the mean free path length. So what the mean free path length means, what is the average distance that the electron is doing before an interaction that can be, Bremsstrahlung or ionization and so on. And this is given simply by this formula. You see that this again is the number of atoms per square centimeter times the cross-section to -1. This gives you the mean free path. Now, if you plot, this is interesting, if you plot the mean free path length of the electron, this is the one for ionization, this is the one for inelastic, for other inelastic interactions, and this is the total one. You see an interesting thing. You see that when you are here for ionization, so the black one, when you are here, you are at 100 electron volt. This is if you remember, this is the maximum of the cross-section for ionization. And sure enough, as you would expect, being the maximum of the cross-section is the minimum of the mean free path. Maximum cross-section means minimum free path. But look at the number. The number is about 1 nanometer. And this is an interesting number because the size of the DNA molecule is about 2 nanometers. So what is happening here is that in this region, about 100 electron volt, These electrons have a maximum cross-section, and their mean-free path correspond pretty much to the size of the DNA. So you will have a high probability of damage induced by these electrons in this energy region. And this is for now. We take a break now, and we will resume the lecture now talking again charged particles, but not electrons. We will talk about ions.